not again, Danai!
Danai the science guy. Science room. Danai the science guy.
Hey, it's Danai the science guy. Today I'm going to talk to you about the physics of ping pong, also known as table tennis. But before I do that, let me give you a brief history. Lawn tennis players wanted to play the game that they loved in the winter. But the problem was, it was way too cold. Therefore, they created table tennis, also known as ping pong, indoors. Surprisingly enough, ping pong did not start in China. It started in England. For the most part, the game stayed the same, except for some minor details, like playing up to 11 as opposed to playing up to 21. Also changing the size of the ball. Originally, it was 38 millimeters, but now it's 40 millimeters. But I'll get to the reason why for that later.
It's really hard for people to appreciate table tennis because they don't understand the high level of play that goes on during a match. Table tennis players use their hearing to react to the ball as opposed to sight. This is because auditory stimuli reaches to their brain 0.03 seconds faster than visual stimuli. Every hundredth of a second counts, especially when a ball leaves the paddle at about 70 miles per hour. While air drag reduces this by 30%, a ping pong ball can get across the 9-foot table in less than 11 hundredths of a second. Believe it or not, this is about 3 times faster than the blink of an eye. Naturally, professional table tennis players slowly move back away from the table. For about every foot, table tennis players get about 13% more time to react. This is why some elite players move as far back as 20 feet away from the table. This gives them about half a second to react. This all shows how intense an actual table tennis match is.
Remember that powerful shot I had before? Instant replay. The last shot I had on Kevin had a lot of power. Well, how exactly do you get more power when you hit a ping pong ball? Well, that's what we're going to talk about today. As you may know, power equals work divided by time. Another way of saying work is force times distance. As you may know, distance divided by time equals velocity. So we can figure out that power equals force times velocity. Meaning, when you're playing ping pong, hitting the ball with more force or hitting the ball with more speed will grant you more power in your shot. You can think power as how much oomph is in the ball when you're playing ping pong.
So, at this point in the video, we're going to talk about the Magnus force. What is this force? Well, the Magnus force is the rising or the sinking of a ball while it's rotating in the air. In ping pong, there are 3 occasions when this happens. One in topspin, one when you apply backspin, and the third when you apply side spin. In topspin, you rotate the ball in the direction you're hitting the ball. In backspin, the ball is rotated in the opposite direction it is flowing in. And in side spin, you hit it across to the left or to the right. So, in ping pong, or commonly known as table tennis, we have 3 spins: topspin, backspin, and side spin. In topspin, we are applying torque to the ball so that it causes rotation towards the right. Now, you might be wondering, why do I have H and L, L and H, L and H? Well, I have a very good reason for that. H stands for high pressure, L stands for low pressure. After applying torque in this direction, high pressure is created above, or in the upper half of the ball. Low pressure is created in the lower half of the ball. Thus, because of the absence of particles in the lower half, the high pressure tries to cover up for the low pressure, causing the ball to spin downwards. The trajectory for this ball looks something like this, commonly known as a parabola. In backspin, we have the opposite thing going on. because of applying torque in this direction, this direction, we have high pressure in the bottom half and lower pressure in the upper half. Due to this, the high pressure tries to go towards the low pressure and causes a flatter trajectory. Like that, and then go straight down because of gravity. So just because this is steeper, no difference. And in our last case, we have side spin. In side spin, we have the ball going towards the left or to the right. In this scenario, we'll take it towards the left. You apply torque on the right, causing the ball to immediately go towards the left. The trajectory for this ball would go something like this. In each situation, the Magnus force is present. Here, we have any ball rotating, applied by a force previously. Now it is in the air. We have two forces mainly, the force of gravity and the force of drag, or air. Now, air splits up into two directions. One, going from here down here, and two, going from here around the top. You may be wondering, well, why doesn't the air just go past it? Why does it stick along with the ball? And that is solely because of friction. Friction causes the air to move along with the ball as it rotates. Now here we're in a little bit of a predicament. The air from here goes downwards, comes up here, and starts rotating with the ball, while the air from up here is clashing with the ball rotating. So in reality, this air doesn't go anywhere, it stops in this area. This air continues, and it comes to this area. Now, this is the major focus point for the Magnus force. This is an air pocket. This causes the ball to move upwards or downwards, based off of where the pocket is. If the pocket is under the middle, then it will go upwards. If the pocket is above the middle, it will go downwards. This is called the Magnus effect. We've shown you what the Magnus effect is. We showed you what spins are, and what happens when you actually hit them and they go off to the side, go straight, come back to you. We've all shown that on a whiteboard. Let us show you now, in real life, in real footage, what happens. My assistant Matt I, he will be showing you topspin, backspin, and side spin in this following video clip. So Matt, please show the audience how to do topspin on a ball. Clearly, the ball changed its trajectory as it got launched from the table to a more lower hit, so it's harder for the opponent to hit back. Now, Matt will show you some backspin on the ball. It drops lower after a while. That means it stays in the air for a longer time, making it harder for the opponent to react. And the third spin Matt will show you is side spin. It might be a little bit harder to see the spin, but when it hits the edge of that table, it changes course to the left. Why? Because he hit it towards the right. All in all, these three spins are very important in ping pong, and we have shown you exactly what they do. So here we have a ramp with a block, and clearly there are three forces acting upon it. And we can say the normal force equals mg cosine theta, because if you draw a triangle, you'll be able to identify that the hypotenuse, and using trigonometry, it'll be mg cosine theta. Fgx will be the opposite. It is mg sine theta. Fgx is the horizontal pull of gravity. And so the sine theta comes from the triangle again. Then we have mg cosine theta times mu, because we have normal force times mu, as you can see, frictional force. And finally, we can derive that mg sine theta equals mg cosine theta times mu, because both forces are equal in static friction. Next, we can cancel out the m and the g because they are on both sides of the equation, thus are irrelevant in this situation. And lastly, we find out that mu equals tan theta. So now we're going to determine whether the coefficient of static friction between a paper clip and a thin paddle, or a paper clip and a bigger paddle or thicker paddle, will affect its spin. You may be asking, why aren't we using a ping pong ball? I have a good answer for that. The ping pong ball gets slidey around too much on here. If we put it, it starts to move regardless of whether we lift it or not. So we can't calculate the theta that we need. So in the first experiment, we're going to use a thicker paddle. In conclusion, it is evident that the paddle with a higher coefficient of static friction or the paddle that is thicker will produce a lot more spin. Now, we have confirmed this with multiple trials, just in case you guys were wondering.
Now it's time to talk about air resistance, also known as the force of drag. Drag opposes the direction the ball is going into. So in this case, the ball is going up, therefore drag will be going down. You can think of it as friction in the air. This is the equation to calculate the force of drag. First off, it's negative because it opposes the direction that the ball is going into. Therefore, it's going in the negative direction. This is the coefficient of drag. This is the reference area of the ball times the air density times the speed of the ball squared divided by 2. Now what we have here is an equation specifically used for table tennis. For simplicity reasons, we move the over 2 part on velocity squared to 1/2. The coefficient of drag in this case is 0.4. The reference area of a ping pong ball is pi r squared. The air density in this case is 1.225 kilograms over meters cubed. And lastly, velocity squared is how fast the ball is going at that exact time.
Remember
Said that they changed the size of the ball from 38 millimeters to 40 millimeters? Let me explain why. The table tennis committee wanted to slow down the game because they wanted to attract a wider audience. The problem at the time is that it was too hard to follow along what was going on because the ball was going way too fast. The audience had a difficult time understanding what was going on in a way. So what they did was they increased the size of the ball to increase the reference area, which in conclusion increases the air resistance, which slows down the ball. This way, more people can watch it easily. As you can see, things just came full circle.
That's not a circle, it's a sphere.
Well, yeah, you're right. You know what? I had enough of this. I'm not even a real scientist.
Wait! Dan science guy. Please stay. People, kids, they love watching your videos and learning while watching you.
You know what? You're right.
Oh, I was just kidding. You leave. Who likes you?
Well, that's gonna be it for today, guys. I hope you guys learned something, and we'll catch you on another episode of Dan the Science Guy.